When we first talked about metal shaping, we talked about the 5 things that we could do to a piece of sheet metal in order to make a part. And one of those things is joining. Well, let's talk a little bit about the science of welding. I think for me, it helps to understand the fundamental science that allows us to be able to do it. And it all starts with the state of matter. And we're going to talk about 3 different states of matter: solid, liquid, and a gas. Solid, the particles are tightly packed, resulting in a fixed shape and volume. On the little square, or the little cube here, the bonds are very strong on that solid. And those bonds being strong, they fix it in its volume and they fix it in its shape. So unless we do something to it, this cylinder is going to remain a cylinder. The bonds are very strong inside of it, and it's going to, the volume isn't going to change either. I could take one cylinder, stack it on top of another, and immediately remove it. I could take this other solid and set it on this cylinder and immediately remove it. I could set it there and immediately move it. The bonds are very strong, and it's going to stay together in that volume and in that shape unless I do something to it. The next state of matter is a liquid. A liquid, the particles are loosely joined, allowing the liquid to conform to shape but maintain a fixed volume. So in that case, we could say that this glass of water here, I'm going to put a fixed volume in it, and it's going to take the shape of that glass. Now, if I poured it onto the floor, I'd end up with a puddle onto the floor. Or if I have it in this bottle, it takes the shape of that bottle. If I wanted to change the volume of it, I just add more. Now, you can't tell the difference between the first and the second one because the bonds between those particles are weaker, and they can mix and intermingle and join together, unlike what happened with a solid. So there's an advantage there. Now, when we think about this water, if I wanted to make this water a solid, how would I do it? Well, I would do it by removing energy from it, energy in the form of heat. And by dropping its temperature, I can then turn it into an ice cube. So we go back to this water, and I freeze it into an ice cube right now, I would end up with one block of this shape. If I were to then turn it back into a liquid, add more water to it, and then freeze it again, it would then become, when I freeze it, it would become a solid, a big ice cube of a different shape and volume. And we use that to our advantage in welding. The last form of matter that we're going to talk about is gas. Particles widely spaced move freely, meaning they have no fixed shape or volume. This doesn't play as big a role in the welding process, but it is something to understand. Because if we take a solid and add energy to it, we can create a liquid. If we take a liquid and continue to add energy to it, we can create a gas. And beyond a gas, we continue to add energy to it, we can create a plasma. And it's something to understand about that process. In our case, the energy that we're going to input is in the form of heat. Whether it be an electrical arc from a TIG welder, or the electrical arc from a MIG gun, or the heat from an oxyacetylene flame. Heat is going to be our energy input to change the state of the steel or aluminum or copper or brass from one to another to allow us to join them. So really what welding is the controlled melting and refreezing of the edges of our parts. On this panel that I did a test weld on, you can see that path right there is where that material became liquid. And when it became liquid, those particles having that looser bond were allowed to link together and join together into this new form. And then we allowed it to freeze back into the single panel. So if we take our solid and we continue to add energy to it, we're going to get to this melting point. At that melting point, we go from being a solid to a liquid. We continue to add more energy in the form of heat. We're going to get to a point, the boiling point, where the liquid then becomes a gas. When we allow it to cool, at a certain point, it's going to reach a condensation point where it's going to go from a gas back into a liquid. We continue to remove energy by letting it cool more. We're going to get to freezing point where it's going to go from a liquid to a solid. Now with welding, we're mostly concerned about this point right here, this melting freezing point, because we need to get that solid up to a liquid to allow it to bond and join together, and then freeze it back into a solid. This is a very old welding book that contains some melting points for different materials. As you can see, raw pure aluminum melts at 1,218 degrees. Steel, on the other hand, is 2,480 to 2,786. There's a variance there because of different alloys and compounds inside of it. As you alloy a material, a metal, you're changing the types of bonds that it has, and you will change its melting point. And that's why knowing that melting point is kind of an important thing in the welding process. So now that we know that the melting point is the point we need to get reached to go from a solid to a liquid, we have to talk about a couple of other things as we put that energy into the material. One of them is thermal expansion and contraction, and the other is thermal conductivity. Thermal expansion and contraction, if we were to take this cylinder, and heat it up, it would slightly grow in all directions fairly evenly, and then if we let it cool off, it would cool off and shrink back down or contract evenly. But in welding, that's not what we're doing. We have a plate here, and we're inputting heat on the joint. Let's see, this is already welded. We're inputting heat on that joint. So at the point of heat application, we have thermal expansion, trying to grow that material's trying to get larger. But behind it, where it's cooled off and it's refroze, we have thermal contraction, and it's trying to go back to its original state. Another thing that we have happen is shrink. In the thermal contraction zone, those crystalline structures that the grain inside of the material are trying to go back together, but now they've had that thermal energy and it's kind of acted like a lubricant, and they can sometimes go together a little better than they were before, and they'll shrink down and they'll pull that material and shrink. This is where a lot of the distortion from our welding process comes from, is the thermal expansion and thermal contraction of the weld as we go. Another important consideration is thermal conductivity. So if we think about this piece of material when we start, it's basically all at one temperature. And we're adding heat energy at one point, and that heat energy is being pulled away by the mass of material around it. So it would be great if I could take a flame and I could take a heat gun and set my flame up to 2250 degrees, or if I could put it to, let's see, steel is 2480 degrees, or if I could put aluminum at 1218 degrees. If I could take a heat gun on that flame and make it perfectly that temperature, it would be great. It would be so much easier for welding. But the problem is, all of this mass is stealing heat from your puddle. Another thing that steals heat from your puddle is your filler. Your filler wire is at one temperature. It's not liquid. And when you dab it into that puddle, it's stealing a little bit of heat in that puddle. And that's where heat control and understanding your melting point and understanding this thermal conductivity, you can better make judgments on how to input heat into the material so that you get a good weld bond without having too much of a heat affected zone. Because there are other changes that happen to the steel when it's in the liquid, or the aluminum when it's in the liquid form. That metal changes when it's in a liquid form and goes back to a solid. But it's important to consider, and it's important to kind of study thermal expansion and contraction and thermal conductivity. This is another area where things like preheating, some parts need to be preheated in order to be able to weld it to eliminate some of this thermal conductivity. Because if it's already at a raised temperature, it's also not going to expand as much, because it expands at a rate per degree of temperature. And inside of the book, we have a linear coefficient of expansion for every 1 degree of temperature rise. And it can be calculated how much that material will change over a temperature rise. And if you can imagine, we go from, let's say the plate is 80 degrees in the shop, and we take it up to 2,500 degrees. That's going to be a lot of expansion, even though those coefficients are very small. Another important thing to talk about when the material is in the liquid state is its reactivity. It becomes more reactive as it goes into the liquid state. So things like a film of oil or dirt or oxygen, nitrogen, carbon dioxide, all these things that are in our atmosphere are things that can mix and become a part of that puddle. Well, you can imagine the boiling point of oil is much lower than the steel. And it will off-gas and create things like little gas bubbles inside of our material. Porosity. Porosity is just little gas bubbles inside the material. Dirt, same thing. It's things that are going to get inside of our puddle and change the characteristics of our metal and cause harm to it. Oxygen, it will oxidize. Nitrogen, when plasma cutting, you can nitrify the edge of the panel and make it extremely hard and brittle, or extremely hard, because nitrogen is added from our atmosphere into that molten puddle at the edge of a plasma cut. And all of these things we have to take consideration of. Most of it, we can take a little denatured alcohol and clean the panel. We can sand the panel and get this dirt and this oil away from it. But the environmental things in our atmosphere, we have to do something else. We have to use something like flux. If we're gas welding, some gas welding requires flux. Steel with gas welding, for the most part, the neutral flame and the consumption of the oxygen and the exhaust from the flame is enough to allow you to weld. As far as MIG and TIG, we use gases, these inert gases. Helium, for instance, or argon, or a mix of argon and CO2. We can use those to shield the environment away. So we know we can clean up our dirt. We took a little bit of denatured alcohol and got rid of our oil. But now we're coming in. We've got our hot puddle here. We're going to do a TIG torch. Here we go. And what we're going to have is these inert gases are going to come and spill out all around. And all that it's doing, spilling out all around, it's protecting our puddle, and it's protecting our arc from these environmental, these atmospheric compounds, the oxides, the nitrogen, the carbon dioxide. It's protecting our puddle from that. And in some instances, it may also be important to add a back purge, like welding inside of a tube or something. You may have to fill that tube with argon in order to protect the backside and prevent from pulling from the backside. These are all things that need to be considered on what process you're using, and in order to create a good homogeneous puddle, in order to create a good strong weld. I'm not going to get much further into it than that, but it's something that needs to be researched and thought about when you get into the process that you're going to use. This weld that I did here it's very difficult to see it. This was just a fusion. It was done with TIG, and there was no filler wire added to it whatsoever. What happens when we do that, the fusion is taking the two parent metals and mixing them and blending them and allowing them to join. But it's also scavenging from both edges a little bit of material. So it's actually slightly thinned out right there. And there's no reinforcement to the weld. So the next consideration that we need is to consider our filler. Your filler should be compatible with your base materials, but it also may need to have additional compounds or additional alloys in it. Let's say this was a piece of stainless steel and I needed to weld it to a piece of steel. They're metallurgically close enough where you could do it, but the fused area or the heat affected zone isn't going to be the perfect world between both materials. So we may have to add a different alloy in between the two in order to make them go together properly and have a good bond or a good joint. So it's just another thing that we have to consider is what filler. Fillers also have other things like oxidizers in them that are designed to pull oxides out of the weld puddle to give you a better, stronger weld. So we need to know the base material, the parent material, when we choose our filler. We also need to know what how the filler is alloyed. They make different types of filler wire with different alloys into it, and you may need to consider using a different one depending on what your parent metals are. The filler is also going to add reinforcement to the weld. It's going to give you just a little bit of, you only want a little bit of reinforcement. So instead of taking the metal away, now we're going to have a little additional metal. And that's going to help us finish this weld out. We're going to be able to come in here now and polish that out and make the weld even more invisible than we could if we had fused it, where we might have a slight low spot there. But it's just one of those things you have to consider. What filler metal are you using? What filler metal do you need? What are your parent metals? And understand that filler metals do have a job. They have oxidizers and things in them that are meant to keep a better puddle and a better fusion. So I've tacked this panel just about every inch. And what I'm going to do is I'm going to fuse across it. I'm going to fuse about a third of it. And then I'm going to add filler wire to a third of it. And then I'm going to add a much heavier filler wire to the end of it. And let's see if we can see what happens to the puddle and see if we can have an idea of how heat conductivity and everything plays a role. So this very beginning part, I only did a fusion. And you can see that I'd had to put less heat input into it because the filler was not cooling the puddle. The next section from here to here, I have a much larger heat affected zone. I had to use more time in order to allow the puddle to get hotter in order to get good fusion. And this is an example of how that thermal conductivity, you can actually see it, because the more time I had to wait, the more heat pulled away from my weld. And finally, when I jumped to the great big filler wire that I have right here, you can see I got more fill, but it also took more time to get to that level of heat to be able to fuse it. Okay. So in the beginning, all I was doing was a fusion. This is just a fusion. And you can see I got 100% penetration. That fusion, I did not have to worry about the filler metal cooling the puddle off, so my heat affected zone is smaller. But as I started adding filler in this section, I still got a complete fusion and 100% weld, but I had to take more time. And with more time, the mass of this panel could pull more heat away. And that's an example of the thermal conductivity. Here, I switched to the much larger filler wire. And that much larger filler wire, you can see I had to take even more time to allow that puddle to transition with the heat of that new filler. And that filler was cooling the puddle, so I had to take more time. That time added to the amount of time that thermal conductivity could take over. If we lay our panel down, you can also see what the thermal conductivity did, what the thermal expansion and contraction. It's fairly mild over here, but as I added more heat as I go, it got much more extreme. And now I have that distortion that now we need to correct. And that's just a really good example of how heat and thermal expansion and thermal contraction and the selection of your filler wire, I think that's a really good example of how it all works. Let's get this panel back to being flat. The thermal expansion and the shrinking of the weld is what caused this. So now let's get it back to flat, and we're going to do that by stretching the panel back out. So we'll move over to the post dolly, we'll get it back to flat, and then we'll go from there. But once again, it's a prime example of heat conductivity because it conducted the heat away. The longer the dwell time I had, the more it could pull the heat, and how the filler and adding that cold filler into that liquid puddle, it changed the temperature, so I had to give it more time in order to allow it to get to that molten state and completely fuse. So I'm going to let this cool off for a minute, we'll move to the post dolly, and we'll get her back down flat. So I can flex this panel back into a certain amount of flatness, but I cannot get it back to flat again. And the reason for that is because as the weld puddle cooled and contracted, we were still expanding over here, but they found better, newer bonds to go to. And what happened was the newer bonds caused a bit of shrinking into the metal. So I fairly flattened it out, but you can see it's not flat. So let's go in and we're going to do a little bit of stretching on the post dolly. Already started to ease it up a little bit. I think a bit of our reinforcement is fighting me, but you can see we're already much straighter and much flatter with just a little bit of stretching of the weld. But we'll get more into that when we talk about metal finishing. But I think that this is a good start to understanding welding and what welding is and some of the processes into what we have to do to join two pieces of metal. I'll do more videos in the future of the actual welding process and maybe a little bit more into the selection of electrodes and everything. But I think this gives us a good understanding of the fundamentals of what's happening. And that's what we've done. We've taken a solid, converted to a liquid, and then refroze it again. And in this example, we can see what the role that thermal conductivity played, as well as we could see what thermal expansion and contraction played and what it did to this piece of metal. But I'm going to leave it there, and I'll see you next time. So here's our part here. This is just a fusion. This is where I added the smaller filler wire, and this is where I jumped to the great big filler wire. As you can see, we got 100% penetration all the way down it. Now, I kept the amperage on the machine the same. I just set it to where I could hold the pedal down and fuse, and then started adding filler wire, and then added the larger filler wire. That way the amount of input of temperature that I was using always stayed the same. What was changing the temperature of the puddle and causing more time was because that filler wire was cooling the puddle off. And that way we could see how filler wire affects the puddle. We could also see what time does, because time is going to give us that thermal conductivity. And this is the best way that I could feel to show an example of that. But it's very obvious where when we were just fusing it, the puddle stayed one temperature. And then when I was adding filler wire, it took longer to heat it up to keep that puddle at the right temperature because I was adding a cold filler wire. And that extra time added more thermal conductivity. And then with the great big wire, it was even more. There it is. And that's pretty much the science behind welding. And as I said, we'll do more videos in the future and hopefully add on to it.